Note that I will be skipping some of the examples, and I will only be choosing examples or problems that are more applicable when you solve your optimization problems in real life. So this example is what we call a fixed cost problem. It's an evolution of the transshipment problem from IE41. If you recall, a transshipment problem is a problem wherein you have a number of suppliers and a number of demand points, and you want to deliver goods from the supplier to your demand point. The fixed cost problem elevates that problem to denote that you may have four suppliers, but each or there are operating costs for each supplier, and you would be incurring what we call your fixed cost. Therefore, you also have to determine which plants to open, if you need to open all plants, or which plants just open in order for you to minimize your cost. So, because it's possible that not all four plants will be needed to meet the demand of your deliveries or the demand of your products. So first, let's not notice the three sub problems below. Let's focus on the main fixed cost problem. So in this case, what do we want to know? We want to know let xij be the number of units from location I, 1 for New York, 2 for LA, 3 for Chicago, 4 for Atlanta, to region J. But we're not only interested to know on the number of units that will be supplied by supplier I to region J. We also want to know we also want to know what locations or what suppliers to open. So that's where our binary variables come in. So we let yi be equal to 1 if supplier I is open. Now for the objective function, we want to minimize costs, of course. So let's first um, minimize your variable cost. So min z, your variable cost will be the cost of shipment from supplier I to region J. So that's 10x11 plus 11x12 plus 10x13 plus 6x21 dot dot dot. The last 3 is plus 5x41 plus 6x42 plus 4x43. But your variable costs are not your only costs. We now have your fixed cost. That's why it's a fixed cost problem, which is the fixed cost of operating a warehouse. So that's plus the cost of operating warehouse 1 or the warehouse in New York is 400. So that's plus 400y1 plus 500y2 plus 300y3 plus 150y4. So we've minimized your total cost, which are your variable costs and your fixed costs. For fixed cost, we've modeled it as such so that when, for example, plant Y1 is open, you will incur, this will become 400 times 1. Therefore, the fixed cost of 400 will be incurred. Conversely, if Y1 is closed, this will become 400 times 0, and the fixed cost will not be incurred. Okay, now for your constraints, this is just, let's first start off with your original or your normal transshipment problem constraints. So the supply should be less than or equal to the capacity of the plant. So for New York, that's x11 plus x12 plus x13 is less than the capacity of 100. For LA, it's the same, x21 plus x22 plus x23 less than or equal to 100, x31 plus x32 plus x33 is less than or equal to 100, and x41 plus x42 x43 is less than or equal to 100. Now, if it's for your demand, it has to be greater than or equal to the demand of the region. So for region 1, that's x11 plus x21 plus x31 plus x41 should be greater than or equal to the demand of 80. X for region 2, that's x12 plus x22 plus x32 plus x42 should be greater than or equal to the demand of 70. X13 plus x23 plus x33 plus x43 should be greater than equal to the demand of region 3, that which is 40. And of course, xij is greater than or equal to 0, and yi is binary. However, if this is the case, or if we retain with these values, this just means that even if y1 is open, even if y1 is closed, if we keep the capacity constraint of y1 to be the same, even if y1, it's possible that given your current combination, that y1 will be equal to 0, but x11 plus x12 plus x13 will have a value. Note that again, if y1 is equal to 0, this means that plant 1 should be closed. Therefore, automatically x11, x12, and x13 should be equal to 0. Or what we can say is that if the demand, that is what we can say is that the demand of a plant determines if it's open or not. So we can just say that the capacity of constraint 1 is x11 plus x12 plus x13 is less than or equal to 100 times y1. This case, if plant 1 is open, y1 will get a value of 1, and therefore your right hand side for this constraint will remain at 100. However, if y1 is equal to 0, which means that plant is closed, the right hand side will get a value of 0, and since x1, x11, x12, and x13 are all non-negative integers, they can only take on a value of 0 as well. So let's just use the same concept for all constraints and for all plants. So we go the capacity constraint of y2 is less than or equal to 100 y2. Again, if plant 2 is open, it has a capacity of 100. However, if it's closed, its capacity will be 0. y3 and y4. In this case, we are assured that if a plant is closed, nothing will come out of that plant and nothing will be delivered outside of that plant. This forms the base of our fixed cost model. Now let's go to the 3 sub problems. A. If the NY warehouse is opened, the LA warehouse should be open. So New York is Y1. New York is Y1. LA is Y2. So in this case, if New York is opened, LA warehouse must be open. We can model this out by saying that Y1 is less than or equal to Y2. How so? If y1 is equal to 1, and we note this, and it has this relationship, what we will get is 1 is less than or equal to y2. And since y2 can only have a value of 0 or 1, it will automatically take on the value of 1. But what's also good about this constraint is that if y1 is equal to 0, it doesn't say that if New York is closed, that LA should be closed. It will become 0 is less than or equal to y2. Therefore, y2 can still take on the value of either 1 or 0. So, for that constraint, if the NY warehouse is opened, the LA warehouse must be opened. That is using this constraint. Next, letter B. At most, 2 warehouses can be opened. This is similar to our at most constraint from the previous example. So we just say y1 plus y2 plus y3 plus y4. At most 2. Therefore, that's going to be less than or equal to 2. C. Either the Atlanta or the LA warehouse must be opened. It means at least one of them should be open. If that's the case, then we say Atlanta is y4 and LA is y2. Therefore, we go y2 plus y4 is greater than or equal to 1, since at least one of them has to be opened. So this example just shows the flexibility and the different combinations that we can use a binary variable. We can use it as an at most, we can use it as an at least, or we can use it as to set different conditions of different constraints. This is why the binary variable is really helpful when you want to formulate your more difficult linear programming problems. So the next set or the next problem is what we call a set covering problem. A set covering problem is basically used when you want to cover a set or cover an area using binary integer programming. So for this example, the treasures of King Tut are on display in a museum in New Orleans. The layout of the museum is shown below with different rooms joined by open doors. A guard standing at the door can watch 2 adjoining rooms. The museum wants to ensure guard presence in every room using minimum number of guards. In the layout below, X and Y represent a door number, and a room letter, respectively. So in this case, we want to cover all rooms by having a guard in each door, and a guard can watch over 2 rooms. So it's a set covering problem because we're covering all the rooms in the museum. So what do we want to know? We want to know if a guard is present in a door or there is a guard in a door. So we let xi be equal to 1 if a guard is present in door I. 0 otherwise. Again, apologies for my bad penmanship. But so for our objective function, it's already stated that we want to minimize the number of guards. So we minimize z, which is equal to the sum of guards. So that's x1 plus x2 plus x3 plus x7 plus x8 plus x8 plus x9, since we have 9 doors. We simply want to minimize the number of guards that we have. So for our constraints, we just have to make sure that the whole set is covered. That's why it's called a set covering problem. So in this case, we want all rooms covered. So our set is room and we want all rooms covered. So we now go first, we do the constraint per set. So since our room is per element of the set rather. So since our set is the rooms, so the element are the different rooms. So we first go with room A. We want room A to be covered, and what guards are in room A? That's simply x1 plus so what guards are in room A, or what guards watch over room A? So room A, that's x1 plus x2. We can see it. Room A has guards 1 and guards 2 guarding that room. And we want to ensure that there is at least one guard, greater than or equal to 1. Why do we put greater than or equal to 1 and not equal to 1? Because it's possible that the minimum set will have both guards have a stand-in, and it gives you the minimum number. I know it might not be the most logical, but given the problem, it's a possible solution. So we just don't want to limit the problem in such a way that we're forcing it to just one guard. Since it's a minimization problem and it's greater than or equal to constraint, it will do its best to just limit it to one guard, but it might be an infeasible solution if you just force it to one guard, since it's possible to have more than two guards. Okay, the next set is room B. Next element in the room is room B. So room B is guarded by guards 1 and guards 3. So room B, that's x1 plus x3 is greater than or equal to 1. And we simply do the same for all rooms. Room C will have you x3. Sorry, that's x2 plus x4 is greater than or equal to 1. For room D, that's x4 plus x5 is greater than or equal to 1. For room E, that's x3 plus x5 plus x6 is greater than or equal to 1. Room F, that's x8 is greater than or equal to 1. Room G, x8 plus x9 is greater than or equal to 1. And for room H, that's x7 plus x9 is greater than or equal to 1. xi is binary. There you have it. For a set covering problem, just make sure that all elements on the set is covered. So you go through, you determine what's the set here is rooms, and make sure that each element is covered by the given conditions. The last example that we will be discussing using binary integer programming is formulating a non-convex region. If you remember, in IE41, the simplex method can only be performed on a convex region. In this case, what if you're faced with a non-convex region problem? The way to do this is to break down your non-convex region into convex regions. And then from there, we do an either or an at most one type of constraint to denote that the variable will either be only in that region or in the other region or on a specific region. So for our example here, let me make this a bit bigger so that it's clearer. We have a non-convex region. So the first step in solving a problem like this is to divide the problem into a convex region or into two different convex regions. Apologies, not just two, but it depends on how many convex regions is needed. The smaller number, the better. Let's first get the lines corresponding to each region. The red line is given by x1 plus x2 is equal to 4. The green line is given by the equation 1 plus x2 is equal to 2. And the blue line is given by the equation x2 is equal to 1. Now it will now depend on how we divide the convex regions. So I would like to divide my convex regions as such. Again, this is arbitrary. I will do the division as this division. This region will be region 1, and this convex region will be region 2. From there, we now define your regions. We now define the bounds of your region. First, let's get your governing regions. Meaning these are the exact boundaries of your feasible region that will make them convex. For that, your exact boundaries for this problem is given by these purple lines. It's your x2 is greater than or equal to 0 constraint, x1 is greater than or equal to 0 constraint, and that x1 plus x2 is less than or equal to 4. It's governing because no matter where your point will fall, where your optimal point will fall, it will follow those constraints. So let's write down your governing region, or governing constraints rather. Again, that's x1 is greater than or equal to 0, x2 is greater than or equal to 0, and x1 plus x2 is less than or equal to 4. So your governing constraints again are x1 is greater than or equal to 0, x2 is less than or equal x2 is greater than or equal to 0, and x1 plus x2 is less than or equal to 4. Again, at any point, these constraints will hold true. Let's now get the constraints for region 1. The constraints for region 1 is defined by these boundaries. I will highlight them in purple. It's this, but that's already x2 is greater than or equal to 0. It's also governed by this line. This is already x1 is greater than or equal to 0. Now let's get this line. That line is also governed by this line, which is already x1 plus x2 is less than or equal to 4. Therefore, the other boundary that's left is this line, which is given by x1 plus x2 is greater than or equal to 2. That's the only additional constraint needed for constraint 1. Region 1 is defined by this constraint, which is x1 is greater than or equal to 0. This constraint, which is defined by x2 as greater than or equal to 0. And this constraint, which is defined by x1 plus x2 is less than or equal to 2. And this constraint, which is defined by x2 is less than or equal to 1. Apologies, this should be region 2, not region 1. Okay, from here, what we do now is an at most constraint, meaning a point can only be at most in one region, either in region 1 or region 2. So if you recall your earlier examples, if you have two regions and it's an utmost region, what we do is we introduce a new binary variable, let yi be equal to 1 if point is in region I. Therefore, what we do is, again, we add a very big variable or very big number m to the sides that is on the greater than side, and append the corresponding coefficient 1 minus y1, 1 minus y2 for region 2, 1 minus y2 for region 2, and again, at most, therefore we have a y1 plus y2 at most should be greater than or equal to 1. Oops. Again, it's an at most constraint, therefore only 1 or 2, at most 1. So we have a y1 plus y2 is less than or equal to 1. At most 1. Now, to explain, again, a point can only be in region 1 or in region 2. So what happens is, if it's in region 1, all of these constraints will still hold true, plus this constraint will hold true. What will happen if y1 is equal to 1 is that you will still get, I will draw a rough sketch, you will still get these constraints, since these are binding constraints, or these are governing constraints. So we will still have x2 is greater than or equal to 0, x1 is greater than or equal to 0 here, and your x1 plus x2 is less than or equal to 4. Additionally, this will also be this constraint will hold, so you will get an x1 plus x2 is greater than or equal to 2. So, and what will happen to these two regions if y1 is equal to 1 is that you will have region 2 constraints will become x1 plus x2 is less than or equal to a very big number, and that x2 is less than or equal to a very big number. So when we draw that in your constraints, it will be somewhere here, and it will be somewhere here relative to this graph. They will just become redundant constraints, and your feasible region will remain as this. It now becomes a convex region. Oops. Now, if y2 is equal to 1, you will still have, again, your non-negativity constraints given by this Cartesian plane. You will still have x1 plus x2 is less than or equal to 4. These constraints now will hold, which means you will have x1 plus x2 is less than or equal to 2, and x2 is less than or equal to 1. So you are left with this feasible region. This constraint becomes redundant, and your region 1 constraint is now x1m is greater than or equal to 2, which is a fact already, and this also becomes redundant. So by doing this, or by breaking it down to convex region and adding an at most constraint, we are able to break it down into two simpler convex regions, which you can now use your simplex algorithm on.